Hey Gen Chem students, so we are going to delve into chapter 6, which is all about how light behaves, essentially. So in chapter 5 we talked about energy in general, and now we're going to kind of connect energy and matter by discussing light. Okay, so light is produced from energy transitions in matter. All right, and the other thing we're going to look at that's really important in this chapter is what we call electron configurations, because as it turns out, those transitions that create light, both visible and invisible light, those transitions happen when electrons change energy levels. So we're going to learn how to organize our electron descriptions so that we can figure out what energy levels are being changed in any given atom. We're also going to use this in the next chapter as a launching point to discuss how chemicals react and why they react. Okay, so understanding electron configurations is one of your primary goals in this chapter, as well as understanding how light can be used in chemistry. Okay, so one of the primary things we need to understand is some of the vocabulary that surrounds waves, okay, because as it turns out, everything moves in a wave. All the matter that we've been studying, all the energy we've been studying, light in particular as one of those examples, all of those move in waves. It turns out for light that the wave nature actually has a really big impact on the behavior of light. And so let's just get into some vocab. First off, wavelength means the distance. So it could be measured in, meters, nanometers, whatever, a whole bunch of different units. It's the distance between the same 2 points on any wave. All right. So here we can use the peaks. Oh, that's impossible to see. Hold on a second. Okay, so there can be a peak-to-peak kind of interaction. You could also do trough-to-trough, as long as it's the same position. You could even do where it's going across the origin in a downward direction, so that would be this point. These 2 points here could be compared. These distances are all the same, though, so whatever measurement you get from peak-to-peak or trough-to-trough or origin-to-origin is always going to be the same distance in any given wave. Now, if you think about a different wave, we can compare one that looks like B, right? And so just conceptually, it's important to understand one of these has a much longer wavelength than the other. So pause the video and take a second and write down which one you think has a longer wavelength. Okay, yeah, so A definitely has a longer wavelength, which means that, if we measured in meters, there'd be a bigger number than B. Okay, and wavelength, by the way, is symbolized with this symbol. It's called lambda. So it's a Greek letter, and it's written, usually when you do it by hand, you kind of make this diagonal line with a little hook on the end, and then you do a little, kind of like an upside down Y in a way. Okay, so that's lambda. It always means wavelength. The units of lambda can be any distance measurement, so meters, nanometers, picometers, whatever you need to use. Okay, another vocab word we're going to use is speed. And when you're talking about the speed of light, we use the variable c. And when we're talking about that, we're talking about the speed with which the entire wave moves through space. So it's kind of strange, all right? So speed and velocity mean the same thing. And as it turns out, these two waves, which look very different when you plot them, these two waves are moving with the same velocity. They have the same speed. And that is true of all the different wavelengths of light as well. All light moves at the same speed, which is 2.99 times 10 to the 8 meters per second. So that's the speed of light. Here, this is actually showing us sound waves. So these are much slower. Sound waves don't travel as quickly and depend much more upon what they're traveling through. All right, and so in this case, we have these sound waves, and it's a good sort of top down. So if you imagine we're taking this pattern and we're looking at it from the top. So the darker areas are like the peak clustering together, kind of coming closer at you, and the lighter areas represent the trough. All right, and so as it turns out, the wave velocity for these two waves is exactly the same. So if you kind of watch how fast any one point, so they've picked purple here to show us, but these points are moving at the same speed, even though they clearly have different wavelengths, right? So this is more like A in the last diagram, and this is more like B. So we have longer wavelength on the left and a shorter wavelength on the right. The other thing to look at here is a related quantity that we call frequency, right? And so if you watch the red dot is actually in the same X position all the time. It's traveling along the Y, so its Y position is changing, but its distance is not changing. It's like if you were standing on the side of a road watching a wave travel by. That's what the X is doing, what the red dot is doing. You can see that the red dot on the shorter wavelength wave has to move much quicker. You might even say it goes up and down more frequently. So this one will have a higher frequency, and the symbol for frequency is either of an F that's kind of cursive, so frequency, or sometimes you'll see the Greek letter nu, which is kind of a fancy V, right? This gets a little, I prefer to use F because we're going to talk about velocity in this chapter as well, and the symbol for velocity is a V, so, you know, I try to use the F instead of the V, but this is not a standardized thing. You're going to run into both of them. Okay, so frequency is the kind of rate at which this dot bounces up and down. We measure frequency in terms of inverse seconds most often, which is also called hertz. So we would have a higher number of hertz for the right hand wave than we would have for the left hand wave. As sound, we would hear this, the one on the right would be a higher pitch, the one on the left would be a lower pitch. In terms of light, frequency is related to color, so is wavelength. And so, just take a second, figure out how are wavelength and frequency related. Your two choices are proportionally, so in other words, if one goes up, the other goes up, or inverse of each other, so if one goes up, the other goes down. This gives us an equation. This relationship gives us an equation, and it relates frequency with velocity and the speed of light, right? So it's right here. Another way to write this will be the velocity of light, speed of light, equals the wavelength times the frequency. These two equations are equivalent. Okay. So if you wanted to find the relationship between wavelength and frequency, you would solve for one or the other. So if we do that, we're going to divide by frequency or divide by wavelength on both sides. And the fact that you have to divide to make these on opposite sides of an equality means that they are inverse of each other. As one goes up, as the wavelength gets big, the frequency gets small. So those are inverse relationships. So from our textbook, you can see a really nice representation of what we call the electromagnetic spectrum. The electromagnetic spectrum lays out all the different kinds of light. We can only see a tiny fraction of that. So from the violet to the red, from about 350 to 400 nanometers up to about 700, 750 nanometers. That's the visible range, all right? And it's a tiny, tiny fraction of the entire spectrum. Those were wavelengths, by the way, because nanometers, okay? So we have on top here the wavelength axis, and it's largest on the right side, and smaller on the left side. So in other words, gamma rays have the smallest wavelength. If we look at the frequency, it goes the other way. The largest frequency is on the left side, and the lowest frequency is on the right side. That's another way to tell that these things are inverse of each other, right? And so it's, oops, hold on. So in terms of wavelength, we are getting bigger going from the left side to the right side. In terms of the frequency, it's the exact opposite direction. We're going from the right to the left. I've already animated in here for you an arrow that also shows the relationship to energy. So energy and frequency follow the same relationship. They're both proportional to each other, and they are inversely proportional to wavelength. So this is a nice thing to keep in mind as you're working. I also added to the figure the pink units that are used for the different categories. So like visible and ultraviolet light tends to be measured in nanometers. Infrared is micrometers, but most people call them micrometers. Microwave tends to be on the millimeter to centimeter range. You can see that because this is centimeters, right? 10 to the negative 2 meters. That would be a centimeter. 10 to the negative 3 would be millimeters. And then also radio waves are measured in generally kilometers or meters. Okay, so this is the scale that we use. And this is part of why we had to learn so many different metric prefixes, because they come into play. Okay. It's a good idea to have a general idea of what kinds of light have high energy versus low energy, and to be able to relate that to frequency and wavelength conceptually. So for example, we want to understand that gamma rays are the highest energy that you can have. Radio waves are the lowest energy that you can have, and everything that happens in between. So in lab,